I got to look at many of the homeworks before class, and so there was one basic thing that I wanted to, well, most people got this all right, but I wanted to correct one thing, and that is for the numeric differentiation. One thing some people did was actually apply basically that definition of the limit, you know, as epsilon approaches 0, so on, and that's just another way of doing differentiation. The numeric differentiation, the reason for that is really you might put that into a program, right? So you have got some computation where you're doing your gradient descent, and you've got some symbolic differentiation that's happened, okay? And you're coming up with a number, and you want to double check it. Numeric differentiation is the way to check it. So how do I check that my computation of f prime of x is correct for something simple like this? Okay, I know nothing about the rules, and I know nothing about whether I got the chain rule right or wrong, not that there's much use of the chain rule here. But in any case, just compute f at one value, right? In this case, we're interested at f prime of 4? Yes. So what is the slope at x equals 2? We'll say 2 here, okay? And so that's then 2 plus a little bit squared minus 2 squared over the little bit, right? So we're just, right, taking a point here, and we're saying let's just go up a little bit and compute the slope by looking at the slope between those two values. So 2.001 squared is about 4.002. With a little bit off to the end. Minus 4 is 0.002 divided by 0.001 is around 2, which looks good. So if we wrote a program that was doing this, and we happened to feed in the x squared, and it came out with a value of 2, here, sorry, let's fix something here. Let's use the rules we know. F prime of x equals 2x, right? So f prime of 2 should be equal to 4. So we have a problem, in fact, and I provided this just to demonstrate the problem. So what are we doing wrong here? So what we're doing wrong is this. So I just took, you know, x plus y squared is x squared plus 2xy plus y squared, but I did it wrong. So I should be using a calculator for this or a computer. That's the whole point of this. Not to do it in my head and not to symbolically do it. But in any case, that should be a 4. Right? It's 4 plus 0.004001, I believe. So now when we do this, we will correctly get 0.004 divided by 0.001, or 4. So we do this to double check ourselves. And because when we're writing code to do differentiation, it's easy to just get it wrong. And it's like, why is my learning not working? Is it I'm calculating my gradients wrong or something else happening? And it's good to have a double check on your gradients. So if you are doing something like trying to do the derivative of the loss with respect to one of your weights, one of your parameters, fix that parameter, and then change and evaluate the loss for a particular xy, and then add a little epsilon to that parameter and do it again. Divide that by the epsilon, and you'll now see this will be approximately partial L divided by partial, in this case, A1. Okay? Some people used, by the way, an epsilon of 1. That's really big, and it was not very close. So 0.1 was still not very close. You need at least a couple digits to get something relatively close to see like 64 is about 64. And then that's good. Nice double check. Questions on that? So if you're using some package that is calculating gradients, assume they did it right. If you're writing your own for any reason, this is such a simple test, and I suggest doing it. Any questions on that? All right, so what we're going to be going through today is kind of a grab bag, sort of a grab bag. So we're going to go through stochastic gradient descent, which we just briefly touched on, I think, on Wednesday. So stochastic gradient descent, and then normalizing. That is, if you've got multiple inputs, so x1s and x2s and x3s, you may need to do some pre-processing on the data to get everything into good ranges. We're going to normalize that input data. This is true not just for deep learning, but for machine learning in general. And then the last thing I'm going to talk about is regularization techniques. So regularization techniques are a way to, one way to look at it is to try and make your model more constrained, okay? To impose more constraint on it. And will that be an approach we'd use to fix underfitting or overfitting? Anyone? Check. Yeah, overfitting, right? If it were underfitting, the model's not rich enough, so we certainly wouldn't want to constrain it even more. We would constrain it if it is too tied to the data we provided it. And so that would make it generalize more. So we'll talk about a bunch of techniques for that. So stochastic gradient descent. Stochastic meaning random gradient descent. And there are three cases we're going to look at. We're going to look at batch. We're going to look at what we might call true gradient descent, and then we're going to look at mini batch. Okay. Batch is what we've been doing so far. So batch, we have our training data set. Let's call it T. Okay? And conceptually, let's say it looks like this. These are a bunch of training examples that we have, 1 through n. So our training loop, let's call it, would look something like this. We would, I'll make this pseudocode, initialize our thetas. Right? Just all of our theta i's. How did we initialize ours in the Jupyter notebook? What did we initialize our parameters to? 0. Yeah. In the case when we're doing deep learning, where we have different parameters that we're using, it turns out we can do just about anything we want except 0. So if we do zeros, we're going to ruin our matrix multiplication. So we'll pick something other than zeros. Commonly, we'll do some random initialization with some constraints. But this is one thing we're going to do, is we're going to initialize our thetas. And then we're going to look at this stochastic gradient descent loop to update this. So what we're going to do is, for all xy pairs in D, we will update, let's call it the average gradient. With the gradient of xy. So we're going to calculate the gradient of xy, and then we're going to update this average gradient. Is the gradient a single derivative? Mo. Is the gradient here a single derivative?
I think so.
Okay. Let me give you the rest of the loop, and then we'll see if we can. So now what we're going to do, basically, we're going to update theta and subtract the average gradient. This update the gradient is just, I don't want to show, adding to a total and dividing by the number. So I'm just kind of hiding those details here. So is theta a scalar, Mo? Not really. Let me try this. How many parameters do we have in our linear model?
I.
Well, in our linear model. So we've got
So
2, right? So when we're updating theta, we're updating two things, right? We're updating theta 1 and theta 2 at the same time. When we're initializing theta, we're initializing two things at a time. So given that there are 2 on this side, how many are on this side?
Oh, there should be 2.
There should be 2 as well. So the gradient is a vector, in this case, of partial derivatives, right? So we've got partial derivative of the loss with respect to A1 and the partial derivative of the loss with respect to A2. Does that make sense? Okay. So this is the gradient. And when we get to our actual neural networks, we're going to be having big matrices of weights. And so our gradient is going to include derivatives for every one of those, for all of our weight matrices. Okay? Does this make sense? This is what our loop looks like. Now, where does the word stochastic come into play here? Brandon, any thoughts?
With the batches. Oh, in this?
In this.
What D is?
The training data set, I mean, it's not random. It gets given to us in a non-random fashion. Someone hands it to us. It could be, so there could be some initialization there. But the stochastic gradient descent sounds like the gradient descent has a random element to it. And in our case, if we're initializing theta to 0, that's certainly not random. So, batch, non-stochastic. Okay? So when people talk about batch SGD, it's like, oh, you mean batch GD, right? There's no stochasticity there. So now let's contrast this. Let's look at the other end of the spectrum, which is what we'll call true gradient descent. Okay, so let's look at true SGD. And when we say true SGD, hey, we mean stochastic, okay? So we're going to initialize theta. We are going to, for all x, y in D, in a random order. Okay? Ben. Where's the stochasticity here?
I guess it's the D we pick.
D is the entire batch. Right. So there's no pick.
Do we not want to like decrease the batch like into a smaller batch?
There's no smaller. Here's what we do. This is so. So for the batch case, number 1, we take them all. For this case, we take 1. Okay, so this is the number 2, true. So we're going to iterate through every x, y, and d one at a time in a random order. Okay? And what we're going to do is update theta minus equals. What do you think we're going to update? Give me a guess. Or how will we update theta? We're going to use the gradient of x and y. In this case, what do? We said, what's the gradient for the first one, for the second one, for the third one, for the fourth one, for the fifth one, all the way through, average them all together. That's the true gradient, right? You want to go up, I want to go down, Raji wants to go down, we're going down. Unless you want to go up more than the sum of how much we want to go down. In this case, we say, I'm going to pick, Ben, do you want to go up or down? Up, right, because that's what we said before. So we're going to make the gradient go up. And then Raji, you want to go? Down. Let's go down. And I want to go down. So we're going to take this little path, right, where we're continually adjusting the parameters based on one of these training examples at a time. And the fact that we're doing it in random order, this is the S in stochastic gradient descent, that we're doing this in random order. And really, I'm sorry I left something off, which is we really have an outer for loop as well. This is for each epoch. And here, for each epoch. So let's say we decide we're going to do 10 epochs. And we have these 3 training examples, you and Raji and me. In this case, we would go through the first epoch and say, okay, you want to go up, you want to go down, you want to go down, let's go down. And in the second epoch, we've adjusted the thetas, right? So this is part of this for each here. Right? Now we've adjusted the thetas, and we'll, again, try these training examples and see what's the gradient. And we'll adjust it once. Go through all of them, check the gradient, calculate the average, adjust them once. Here, we're just going through first epoch, we check you and you and you in random order. Next epoch, we check you and me and you in random order. And every time, we're updating the parameters. Does that concept make sense?
How is it going to be different in the end when all the points are iterated through?
How is it going to be different is a good question. So in this case, let's say roughly the same, except the stochasticity here will allow us perhaps to explore part of our loss space that we might not explore here. This one is going to be more jaggy. Our losses are going to be going up and down. Here, the only reason, so you guys let me get away with this. Theta minus equals average gradient. I'm missing a term here. Anisha? Or anyone? What term am I missing here? Jake, the lambda. The lambda, which is lambda. What happened to my lambda? Trace me a lambda for me. Yeah, that's it. Okay, right. My lambda. There it is. I'm sorry, it just... And here, and you guys did a great job of tracing in the air, by the way. So our lambdas are our learning rate, so that we don't take too big a step. My question was going to be, what do we know about the loss here after every epoch? Are we guaranteed that it's going to be going down, Matt? In this case. So, and when we talk about the loss, let's say the loss across our entire training set. So if we actually go through, update theta, and then calculate our loss across the entire training set, has it necessarily gone down?
No.
How could it fail to?
If the lambda is too large, you could overstep.
Exactly. If the lambda is too large, we could shoot kind of past the minimum we were going to. If our lambda were small enough, then we would be guaranteed our loss would get better across all the trainings. What about here, Ali? Are we guaranteed? So if we went through at the end of the epoch and said, okay, what's the loss across all? Let's not say that. Let's say every time we go through this for loop, every time we update these coefficients, we went through and recalculated the loss.
I don't think so.
What if we had a small learning rate? So in this case, if we have a small enough learning rate, we're guaranteed our loss is going to go down. If we have a small enough learning rate here, we guarantee the loss is going to go down. Okay, so it's a not 100% confident. You don't think so. You don't think so is correct. So your thought is not correct. Let me give you an example why. Let's say this same case where we've got just 3 training examples. And I don't know why I like to personify them, but I do. Again, it's Raji and Ben and me are the training examples. And we choose Ben first. And Ben says, go up. But we want to go down, right? And now we go through and we calculate the loss. Your loss is now better, right? Because you wanted to go up, and we went up in the coefficient. But ours are worse, and so our total loss is worse. Okay? That is, our average loss is worse than it was, because we just went in one particular direction, and who's to say that was the most common direction everyone wanted to go? The advantage then of here is we know the gradient's in the right direction. We know when we're updating the coefficient that we're updating it in the right direction. Roger.
But even though, like, in a particular scenario, the loss might not go down, once you exit the for loop, shouldn't the loss have gone down?
In expectation, you would expect it to, but I will give you an example why not in a moment. Okay, so we're just going to kind of hold off on that for a second. So we know we're going in the right direction. Here, we don't necessarily know we're going in the right direction. However, let's look at the very beginning. You initialize theta. Garbage theta, right? It's just not doing you very well. We wait until we calculate the gradient for all of the training examples before we update it. Here, one time we say, well, we can make it better at least. And the next time we make it better, and the next time we make it better, and so on. So it's very possible that at the end of the first epoch, we might have a much better set of coefficients, a lower loss than we did here. Because we started in the right direction, and we got a lot of cases where we kept going in what might very well have been the right direction. Certainly the right direction according to that particular training example. So if we have a training data set of 10,000, here we make one update to the coefficient. Here we made 10,000 updates. Likely we're going to be in a better position. Ben.
So for that reason, is it oftentimes that like true stochastic gradient descent might be used earlier in training, and you might switch over to just straight?
No one uses either of these. So we'll get to our hybrid. What's the downside of this one? Oh, Jack.
Since the average gradient, maybe listening, also if you're listening to basically all your things equally. Maybe you want to listen to certain sets or more. So you're sort of weighting everything the same.
Yeah, you're weighting everything the same. Aren't you doing the same thing here?
Like it's an issue with both. I mean,
Yeah, it's an issue. It's an issue in both, and the only real way to deal with that would be like if you care about something more than others, replicate in the data. Like you think this training example is really important, replicate it a bunch of times so it sort of has more. It will count more. This for loop is expensive, right? Updating all these. If this were free to calculate them all, then sure, do them all. It'd be great to be able to do that. But it's quicker to go do this. So it's quicker to be updating. Let me show you why random order is critical. And this is an example from someone's thesis last year, okay, that I was a reader on. So she had a bunch of training examples, and we don't even care what the x's are, okay? The x's don't particularly matter what they are. But she had predictions, right, the y's were either 0 or 1. And so she had a bunch of training examples that generated zeros and a bunch of training examples that generated ones. Okay, created all this, a big CSV file, that's fine, and then went to train her machine learning model. And what happened was, after training, it would have an accuracy of 50%. Now, if you were randomly flipping a coin, what sort of accuracy would you get in predicting between a 0 and a 1? 50%. So that's how good it was. It turns out that the training was not in a random order. It was in this order. So let's say you were training and you just went through individually one by one. The answer is a 0. And the answer is a 0. And I'm going to tell you again, the answer is a 0. What are you going to start predicting? 0. You don't even need to look at the input, right? It's just, oh, I should predict 0. And if we do this, 50,000 times, you're going to pretty soon get the idea, all I need to do, forget the input, just say 0. Until all of a sudden, wait a second, the answer is 1. Uh-oh. Well, I'll move a little bit more towards 1, but I'm going to still predict 0. Oh, we get another 1. Okay, I'm slightly more likely to predict 1, but I'm still going to predict 0. Until, after a while, you're going to start saying, forget 0, I'm going to predict 1. And at the end of this, you're predicting 1, let's say. Okay. So if you have a predictor that predicts 1, what sort of an accuracy is it going to get? If we assume equal numbers, 50%, and that's what it was doing. So basically, we just trained to predict 0 for a while, and then move, and then predict 1. And the solution is randomize it. And it turns out that we thought that the package we were using would randomize it, and it didn't. And putting in that one change, all of a sudden it started learning. Okay, so really important. So if on one extreme we take the entire batch, on another extreme we just take a single instance, the middle approach is what we'll call a mini batch. So we'll take we'll initialize theta. We'll go through each epoch. And then for xy, let's just say for mini batch in B, D, and this is a random subsets of a certain size. So let's say we have a data set of 10,000. We might do a mini batch of 100. That is, we're going to break up this into pieces of size 100. Okay? But in a random order. So probably the easiest way to do that is just randomly shuffle this and then take 100 and 100 and 100 all the way to the end. And the last one may be slightly less than 100.
When you mini batch, are all your mini batches the same size?
All except the last one, because it may be smaller. So this is, let's say, mini batch B, and then we do the same thing. For x, y, and B, update the average gradient descent, the average gradient. And then, after we're done with the entire batch, theta minus equals lambda, that I now remember how to write, times the average gradient.
Do you replace when you're taking subsets?
Without
replacement?
Yes, without replacement. That is, we are never looking at these again in the same epoch, right? And then never looking at these in the same epoch. And similarly, within the mini batch, the randomization, does the randomization matter within the mini batch? Matt?
Yes.
Because?
Well, I think similar to previous example you gave, like even in that small mini batch, if it's not randomized, then like you're not really updating to the average.
So let's look here. Right, this is the code that's dealing with the mini batch.
Uh-huh.
What are we calculating in the mini batch?
Updating the average gradient.
So does the average gradient matter? Does it matter the order we visit them if we're calculating the average?
No.
Yep, correct. Ben?
Even if we weren't calculating the average, haven't we already randomized them by randomizing all of them and then just cutting off?
Consent, yeah, so yes, if we did randomize the order, if we randomized the entire thing, we did randomize these as well. Those are sort of implementation details, but it does kind of matter, do we care about the order within it? So conceptually, we don't care whether it's randomized or not, because all we're doing is calculating the average. Okay. How big do we make the mini batch? Any thoughts? Anyone? Yeah, Josh.
You like the square root of the total size of the list.
Square root of the total size of the list sounds kind of attractive in the sense that you have the same number of batches as you have batch size. And that could work. What would we call the name? So we have a batch size, right? We have number of epochs. And we have batch size. Both of which are things we need to decide on. So what are they called? Hyperparameters, right? So yes, we get to add more to our hyperparameter decisions, right? So when you go read a paper, it will tell you the learning rate they use, the batch size they use, the number of epochs they ran, and so on. It turns out that there's a very practical answer to the batch size. It's as large as you can make it without affecting this loop's running speed. That seems kind of crazy, right? If you have a batch size of 2 and compared to a batch size of 4, doesn't this take twice as long? No, why not?
Because you have like a cache or a
Okay, you have a cache, that's one thing. What else?
Each time in the menu, actually, we have to update the gradient.
You do have to upgrade gradient, but for this part right here, just calculating the average gradient. How is it we could increase the batch, the number of elements in B, and yet not change the running time of changing this average gradient? You have a,
Size complexity as well. Just in general. Size complexity. Just like
say more?
The amount of memory used in general.
Okay, so the amount of memory, if each gradient calculation took some memory, then you might be constrained by the amount of memory. So I'll give you one possibility. Maybe this is the number of cores you have in your computer, so you can run these all in parallel, right? So it's just as quick to calculate the average of 10 instances as it is 64 on Knuth if you've got all 64 cores. But actually, what if we had a lot more cores? What if we had, I don't know, 1,000 cores? Do we have machines with 1,000 cores? Like, do we have access to them? Do you? Do you play video games? You do. What do you have?
I have a GPU.
You have a GPU. How many cores on that GPU? A lot, like 1,000 at least, probably. So if we had, let's say, a system with a bunch of things that could simultaneously, and GPUs are ideally suited for calculating the same thing in parallel on multiple different inputs, which is exactly what this is going to be, right? We're calculating the same, in our case, linear f, but in the future, a much more complicated f, but still something that can be done in parallel on all sorts of these. And there, what we're going to be limited by is probably the GPU memory. Okay? So increase the batch size until it's really the mini batch size, but we don't really call it the batch size. So it's the mini batch size until you run out of memory on your GPU. So just keep doubling it till you run out of memory, and then come back till you still have enough memory and use that as your batch size. Okay? So it has, we're basically doing like true stochastic gradient descent, except we're speeding it up by a factor of whatever our batch size is by doing these in the same cost as we're doing one calculation of gradient descent. We'll see some more of that. Questions? So
So which part can be done in parallel?
it's this part that can be done in parallel. The updating the average. So really what it is here. Update the average gradient with gradient of xy. It's this calculation of gradient xy that's the key. We calculate all of those in parallel. Okay? All right. So now let's look at normalizing. So in normalizing, we can normalize inputs and also normalize outputs. Let's look at the idea of inputs. So let's say we are predicting house price given square footage and square footage and number of bedrooms. These are correlated, but who cares, right? So, okay. So the square footage is in what sort of range? Leo.
Some domain, I guess, like, maybe we can do like 1,000 square feet, so an acre.
So acres are 1,000 square feet, like for a house size.
Yeah.
That's a small house, but it's a reasonable house size. So we know we're in a range somewhere, let's say from something to something, and 1,000 is in there. Low end for a house, any guesses? If the size of this room is 700 maybe? Like a tiny house. Let's pick 100. Okay, that is really small. Okay, well, your dorm room is probably not much bigger than that. And at the top end, 5,000. So let's allow Bill Gates to be, part of this. So let's say 50,000. Okay, and number of bedrooms is in the range. Let's say we'll just call. Well, I guess there are studios and something, so it could be 0, let's say, bedrooms, all the way to, let's pick this one, 20, yeah. I'm going to say 50, just to mention, right? Normally, this might be from, 1,200 to 3,600, let's say. That must be your most common range. And your common range of number of bedrooms might be one. If it's a house, we're saying it's a house. I've never seen a house advertised as 0 bedrooms. In apartments, it's studios, but let's say 1 to 6. You never see 1 to 6 bedrooms. But we have different ranges here, and also different scales. Why the heck does this matter? Well, let's say our model is let's just make it a simple linear model, okay? So we're going to do something like f of x1, x2 equals a0 plus a1, x1 plus a2, x2, right? We could make it higher term, right? We could have an x1 squared factor, or maybe even an x1 times x2 factor, but let's ignore all that. So it's a very simple model. And my question is, and we could use a loss, which is the sum of squares, right? So the loss for a single instance is squared, and our total loss will be sum of squared, or average. So my question is, what is partial L, partial A1? This is Ben? X1, so that's this factor here, and
times 2, the whole thing.
right, good. And A2, Santi,
A2 times the same. Oh, sorry, X2.
okay, I'm with you. I thought I maybe misheard for a second. Yeah. All right. All makes perfect sense. X1. If X1 is the house price, how do X1 numbers compare to X2 numbers? So X1 is the house price, X2 is the number of bedrooms. Willow.
The house price is more than the
House price is more, like by how many orders of magnitude? 2. Well, let's see. So we're between around. Yeah, it looks like around 3 orders of magnitude difference. So therefore, this gradient is how much bigger than this gradient in general? 3 times. No, not 3 times. 3 orders of magnitude bigger here than here.
Do you mean square footage and not house price? Or
I meant square footage. So if I said house price, yeah. So this is Y,
yeah.
and these are X1 and X2. So let's look at a picture. So let's say we have equal gradients. So we have equal gradients in an X direct in X1 and X2. So we've got let me change something for just a second. All right. So this is supposed to represent our loss function. And looking at the gradients. And here we've got contour. I don't know why it's still computing, but in any case, we've got a contour map. Is everyone familiar with contour maps? Right. So it's basically we have a circle at the same elevation, let's say, right? So this is all represents one elevation. This represents one elevation. This represents one elevation. And so this is, when we're looking at it, we can't quite tell whether they are increasing or decreasing. So this is either a cone or something kind of like this, upside down. So if we are here and we look at the gradient, we have in the x direction in here and the y direction in here, and we just go directly towards the center when you go on the gradient. Okay? But if we stretch it, if we have instead something that looks like this, okay? Where our gradients are very different in magnitude. Okay? So if we look, I'm going to call this way east-west, and this way north-south. Okay? So in the east-west direction, is the gradient high or low? That is the slope a lot or a little? In this direction. It's low, right? It's flattish. It's pretty flat. And in the north-south direction, on the other hand, the gradient is high. So let's say we're here. So we've got our contour map. something like that. And we're trying to go here, right, to minimize the loss. And we're, let's say, I'll use a colored chalk here. We're here right now. This direction is a high gradient. So this represents, in our case, x1 or x2? Anyone? x1. This is x1. And in this direction is x2. So are we going to travel? This part is the same, right? So the only difference between these two is the difference in x1 and x2. Are we going to travel more in the north-south direction or the east-west direction? Jake.
Probably not south.
In the north-south, because here we are, and we look and we say we have a mild gradient here, and we have a head gradient here, and in this case we're going to go 3 orders of magnitude more this way than this way. So we're going to go, let's say, like this. A little bit to the left, and a lot up. Okay. And I don't want to pick that one quite like that. Let's say we even go to here. All right? And then the next time, we're going to go maybe to here, and then to here, and then to here, and then whatever. Okay? Back and forth, making small steps this way, and large steps this way. Whereas, if we had more of a bullseye, and we start here, we're going to go kind of in that direction, right? Even if they're slightly different, if they're in the same order of magnitude maybe, then we're not going to have these wild gyrations. Does that make sense? So the problem is, these derivatives are different based on the scales of the inputs. And it doesn't make really sense why it should be. It should be that I could scale any input, it seems like, by a factor of 10, or increase it by a factor of 10, and it shouldn't change how it learns. So we're going to do that. We're going to scale our inputs. We're going to normalize our inputs to avoid these differences in scales of the various things that are coming in. Questions on the concept? Okay. How do we scale? Here's one thing we could do. We could look at the endpoints. Well, we could just sit there and say, what seem reasonable values for the ranges for these inputs? Or we could just say, let's look at all of our input data. That tells us a range. Let's use that range. And maybe our input data includes, a Bill Gates mansion, includes a tiny house. So we have these two different sizes. It includes a studio, and includes that same Bill Gates mansion house. Okay? So we have range from 0 to 50, 100 to 50,000. And then we could just scale, we could scale everything, scale and transform to the range 0 to 1. Right? Subtract 100, divide by 50,000, or do that. Yes? Here, how would we also scale from 0 to 1? Susan. How do we scale from something in the range 0 and 50 to something in the range 0 to 1? Divide by 50. And we don't have to do any transform because our left side is 0. So that would make things better. Does that make sense? So this is what that basically means is we're saying if we have an incoming x1 and x2, we normalize x1 equals x1 minus 100 divided by 50k, and x2 equals x2 divided by 50. So in this same rough range. We have to do this during training. When else do we have to do this? Nick.
Before I can pre-process it.
So we're going to pre-process our training data set, right? Any other pre-processing we need to do besides our training data set? Validation. We got to do our validation data set. And when we're actually out in the wild, right, actually making predictions, if someone gives us a square footage, we better subtract 100 and divide by 50,000 because that's how this thing was trained. It expects that.
Is this,
Same thing.
would it be the same as adjusting the lambda? Can we, like the lambda in each direction? It seems like we're transforming the data set as well.
So that's a good question. What we have looked at, just subtracting lambda times the gradient descent, is the simplest possible optimization. Right? You remember in our diagram where we go through and we feed in and we calculate the loss and we have an optimization and update? This is the simplest possible optimization, where we just update every parameter the same way. We will be looking at different optimization strategies that have the equivalent of different lambdas for each weight. And that could... I don't think it would obviate the need for this, but it would make it better. Did you have a question, Danny?
No.
Okay. All right. So this will help, but it's not perfect. And the reason it's not perfect is if we look at our range between 0 and 1, let's see how I want to do this. I guess what I want to do is a graph from 0 to 1. We know that all our training data belongs in this range, right, from 0 to 1. Do we know that all of the validation data belongs in this range? No. We could have, instead of Bill Gates' mansion, Larry Ellison's mansion in New York City that costs even more. Sorry, that doesn't cost more. That is larger. Okay? And so we could have something like a 1.1 or 1.2 or a 2.0 for 100K. But in any case, let's say we look at this. And let's say if we looked at kind of a histogram, it looked like this. And this is the square footage. And we looked at another histogram for the number of bedrooms. And it looked like that. Hello?
Why would you not normalize it before splitting it into training and validation data? Like if you have the whole data set, then because if you do
So that's a
that-
good question. If you want to be finding ranges of normalization, then yeah, it makes sense to look at all the data you have to do that. Sure, I like that.
Can't you look ahead bias by doing that though, if you normalize with your testing data?
Can't you?
You get look ahead bias, so like what happens is like, let's say that your testing data has like a really large value in it. Or yeah, your testing data has a really large value in it, and then you use that to normalize. Now your algorithm knows that it has that potential value.
Okay, I will retract. You're right. We are providing some information to the learning that could make its validation look better. If we have a bunch of data on one axis, on one of our input values that is close to 1, and on the other input, x, the other x, it is closer to 0, we've still got a problem in magnitudes, right? Here maybe it's only an order, 2 times difference, but it's still there. It'd be nice if we could have somehow, if this is what our data looked like, that kind of the most common purples and the most common, whatever this other color is, were the same values. So the normalization that's normally done is we subtract the mean where x1 bar is just the mean across all of the x's in the training data set. Okay. So now what we know is we have 2 mean values. They'll come in at 0. Right? But our scales could still be off. Right? We might have, so now we've moved this over to the left. and we're actually centered at 0. So we have something like this. I'm trying to remember what it looked like, and I don't very well remember it, and we have this one that looks like that. Over to the left, because there's more stuff here. There's more over to the left, and so our mean is a reasonable mean. We can make that so this mean works. Okay. But the problem is, we just got new data. We got a new training set. So let me redraw this. This is like that. Okay? Same means, but what's different about them? The variance is very different, right? The standard deviation is different. So what we're going to do is translate by the mean so that we're centered at 0 and divide by the standard deviation. Next one. So if we do this, Sally, what does a value of 1 represent?
The difference between the mean and the base value.
So it's not going to be the biggest value in this case. 1 would mean, so we're stretching this, we're shrinking it. So let's see, if 1 is here, can't easily shrink and grab this. So 1 represents 1 standard deviation above the mean. -1 represents 1 standard deviation below the mean. And 2 standard deviations above, 2 standard deviations below, and so on. There's no guarantee these are normal distributions, right? But we do know some bounds on what percentage of our data is going to be 1 standard deviation, 2 standard deviations, 3 standard deviations away, right? So this gives us data normalized such that the x1s and x2s should be in roughly the same scale, same values. No matter what machine learning algorithm you're using, you're going to want to be doing this normalization. What happened? All right. We have time just to get into regularization techniques, just a little bit. But I expected this to go on anyway, so this makes sense. So let's look at the first regularization technique. So this is going to be sort of very straightforward. I am not going to do that. I'm going to start with data augmentation. So we're going to skip the loss function. And I'm going to say one way you can increase generality, okay, decrease validation error, is to increase the number of data. Increase the amount of data you have, right? More data is going to make you generalize better. The reason we don't have more data, usually, is it's expensive to generate. So, here's my idea. Let's say we're doing a cat detector. Okay, we take in pictures, and we say yes if it's a cat, and no if it's a not. So here's a cat that's coming in to it's one of our training examples, right? So this is x, and y is 1. I'm going to say, if that is a cat, then if I took the mirror image of it, so this is some x prime. This is also a fake training example, but is this a good training example to feed to a learning algorithm? This seems really, could it see cats facing to the right? Yeah. Would it look like this? Yeah. So this is a kind of augmentation. So here's what I want you to do. Work with a partner for 90 seconds and see if you can figure out other augmentation techniques you can use. I've got this cat picture. How, in any other ways that I can generate a fake image to feed into my training to sort of generate more. So one was flipping horizontally. Work with a partner, okay, the person next to you, and just come up with some others, write them down, brainstorm any possibilities. But write them down. Okay, 30 seconds. Come up with 3 more ideas in 30 seconds. All right, I'm going to start in the back. For your group, give me one that's not on the list here. Crop. So you could take, I know, and crop it, and you've got just a smaller one, right? That's still a cat. What about, though, if the cat's face got cut off? Which we only do in the computer, right? We do not do that in real life. So if the cat's face got cut off, and it was like that, is that still a cat? I mean, you and I would look at it and say, it's looked like a cat with its face cut off, but yeah, it's a cat. So cropping sounds good. You guys, Mo, Josh.
You said we play around with the color a little bit, so maybe a few shades darker.
So adjust
The color.
the color or the brightness?
I mean, I guess that's, yeah.
Brightness, okay.
Um,
You just get one. Ezra,
Maybe photo quality,
tell me more what that means.
like the amount of pixels in the image, so you'd decrease it just in case, unless all of them are the same size images.
So you'd like decrease the resolution, is that what you're thinking?
Yeah.
Okay. Sally.
We said that you could add like random kind of noise to the photo, like you can put, I don't know, shapes on it or something like that.
Add noise. That's a good one. Well, they're all good so far. Morgan. Yeah.
Maybe like distort it in some way. So
Give me a distortion.
stretch it out so it's a longer cat.
Stretch it out. Okay. So stretch. I'm going to just say that. Okay. And
Maybe a grayscale.
grayscale, sure. So black and whiteify it.
Like rotate it,
Wrote to how much?
90 degrees.
All right. So we definitely do sometimes see cats in those direct, if you're not portrait or landscape. So you could do 90 degrees.
There's no reason that you can just do one of these things. You can do a combination of them.
Okay, combo. Daniel?
You could compress the image.
So if you have, so you could get like JPEG, like you could JPEGify it.
Yeah, or you could yeah.
So, and that makes sense, right? Because we might very well have, this might be a raw camera image cat. And we might come up, so.
Or you could like cut out some rows or columns occasionally, and then change the content significantly.
All right, I'm going to go with JPEGify because I like that one. Go ahead.
We could flip it vertically.
Okay, so this is an upside down cat. It sometimes happens. So I'm not sure if you guys are aware of the anti-gravity device. Okay, so you take a cat and you strap buttered toast to its back. And then when you drop it, we know cats always drop on their feet, but buttered toast always lands buttered side down. And so they'll just hover there indefinitely. So this is vertical flip. If you're doing like a satellite view, vertical flip you do every day, right? Because you're looking down from the top and it could very well be each way. Cats do sometimes come through the air upside down, so that makes sense. What you guys got?
Make the background white.
How would you determine the background? The good thing about these is it's fairly easy. So yeah, making the background white is a hard one. You guys? Zoom, sure. Zoom in on particular parts. And for rotate, let's just do X degrees, right? Do we know how to rotate 2 degrees? Sure, we can do that. So all that is ways we can augment our database. For every input data image, we could have hundreds of other possible images. And we can just use a little bit of random rotation here and some zoom or a vertical flip and some just combo. Anyway, that's it. We'll get to the rest of regularization on Wednesday. And I have office hours just after this.